Our main presentation is Dr. Ryan Oelkers from the University of Texas, Rio Grande Valley. So it must be really nice and dark out there. So we're kind of jealous of these dark skies. Dr. Oelkers also collaborates with the Munnerlyn Instrumentation Lab to design new astronomical instruments. So that's pretty awesome. So maybe there'll be some interesting comments about that during his presentation or questions. And he also has considerable experience in astronomical survey management, targeting and cadence coordinator for Milky Way Mapper. And tonight he'll be talking about exoplanets and how they have shaped our interpretations of stellar variability, so variable stars. So without further ado, I want to welcome Ryan Oelkers to the club, and we look forward to hearing your presentation, Dr. Oelkers.
Well, thank you guys for inviting me. I really appreciate the time to talk to you all. I won't say that I'm a Houston native, but I lived in Houston for a good amount of time. I guess I've split half my time in the Northeast around sort of Philly area and half the time in Texas, in Houston until recently when I moved down to Brownsville. So I'm a little bit jealous. You guys said you had good skies in Brownsville, but I'm a little bit jealous that you guys are still in that sort of Houston metro area. But yeah, anyway, so what I'd like to talk about today is some work that we've been doing using some wide field telescopes to try to understand how stellar variability really affects exoplanets. And most of this work wouldn't have been done without a lot of opportunities to study exoplanets and using some new equipment. Okay, so I always like to start sort of back in time a little bit because when we talk about time series astronomy, particularly like professional astronomers, we like to sound really cool. But time series astronomy is not anything that's new. We've really been doing it since antiquity. You know, I don't know anyone who's never looked up to the sky, seen it once and said, you know, I'm good. I've sort of had my fill. I don't need to look again. I think we'd like to call those kind of people theoretical astronomers. But no, right? You like to look through a telescope multiple times. You'll look at Venus one night, then you'll try to look at Jupiter another night. You'll try to understand what's going on. And so we can actually move and record sort of how things are changing in the sky. The difference between the observations we've made in antiquity and sort of the observations we're making now is that we're using sort of a large scale number of these really small telescopes. So a lot of the work that I've done don't even use telescopes that are like 2 meters or 1 meter. There could be 10 centimeters in size. They could be a couple inches in size, even just kind of like Nikon lenses put on a CCD. And that is useful because they can get really wide views of the sky, take a lot of observations to really study how stars are changing. And so we've actually been able to move away from, you know, this idea that Galileo had where he was, you know, drawing the moons of Jupiter and how they changed in their notebook to something much more sophisticated like the video on the left. So what you're seeing is observations of an actual variable star taken with the TESS instrument, which we'll be talking about a pretty good amount. And what was done was the first image in a sequence of a couple hours was subtracted from all the other images. Variable stars, sort of as we know, they're basically fighting to maintain some type of hydrostatic equilibrium as the internal parts of the star get older. And so that ends up in this light curve, which is either sinusoidal in some cases, or it looks like heartbeats for specific kind of stars, but the colors of the star change as it sort of expands and cools with time. And so we know that a lot of objects like this are super dynamic. And it turns out if you were to make the sort of the same video we have on the left for a very large portion of the sky, which is what I have here, this is what you'd end up getting. And so at first glance, it's pretty crazy to looking at all these things, but it's not super complicated. So we've taken the exact same scenario with the previous slide. So we took one image and then a sequence of image, and the first image we've subtracted from all the other images, and we've made it into a movie. And so what you can actually see is that there's a lot of these blinking objects, a lot of these variable stars in the sky. All the sort of yin-yang looking things, those are stars like our sun. And I mean that in a sense that they're not really changing with time. So the subtraction doesn't look very good. But you see a lot of the blinking things. You see this big white sort of blob moving across the bottom. That's actually a comet. If you look sort of in the middle, you'll see sort of a smaller object that's moving, likely an asteroid. But the sky itself is super dynamic. There's a lot of nerdy stuff too about CCD you can actually see by looking at this image. But it just goes to show the point that there's a lot that's going on with the sky and a lot that's changing with time. So we really need to kind of understand just exactly what is going on with all of these stars if we're really going to understand planets. And of course, this is the star there on the top, if you were trying to guess which one was the star from before. So what does this look like in terms of like light curves and things that we can actually measure? So you can imagine back in the 90s, you may have been a professional or amateur astronomer. You have like your Nirvana, t-shirt and your jean jacket, and you get some time on Hubble, and you want to take some images of a star, and you take them, and this is what the light curve looks like when it's just looking kind of like time series. But you're smart enough, maybe if I fold on the period of the star, you can actually get what the variability looks like. So you can look at sort of an RLIRE. But back then, when we were looking at objects, you weren't always taking data continuously. And so you kind of had to use these models, which is sort of the solid line there, to really get an understanding of the physics of what was going on in the star. Now, current times, you may still have your jean jacket and your Nirvana t-shirt because you don't want to let it go. But the data that we're getting is actually in real time, continuous observations. And so this is an observations on the top here of a similar type of RLIRE star. But now if I zoom in, we see that we basically have an observation that's being taken every 20 seconds. And so we no longer need that model to really try to understand the physics of the stars. We can actually just use the data itself to understand what's going on. And then we can begin to look at it and say, there are these weird wiggles and bumps, and what does that mean? And what could that sort of effect of the variability mean on the solar system? And really to kind of hammer this point in the 2010s when I was in graduate school, we had a good number of observations of things, but they were basically from the tens to hundreds of thousands in terms of just basic measurements of stars, like the distances to stars, the masses, radii of stars, like really good, precise stars, understanding how many planets were around different stars. And just in 10 years, so the turn of the last decade, we basically increased everything by a factor of 100 or more. So now we're kind of inundated with a lot of data, and that's good because it allows us to really make precise measurements of things. And it's something that even I didn't realize when I started graduate school, was that we just didn't have a lot of good measurements of stars. And now basically any star you can see with your eye or point a telescope to in the ground, we more or less understand its distance, its mass, and its radius. So now we can really try to, figure out what's going on in each one of those solar systems. But of course, that has moved us from sort of the classical idea of an astronomer of, someone working at a telescope, building instruments, tinkering, staying up late, getting a little eccentric because you're never around people, you're always staying up at night, to the more modern idea of an astronomer, which is you're still eccentric, you're probably staying up all night, and you're still, kind of secluded in your room, but now you're looking at numbers and you're doing a lot of database work because we've really moved from a lot of observations being taken by the astronomer to observations being taken by survey satellites, and then the astronomer tries to understand all the data. So a lot of times when students want to work with me, the first thing I ask them is, do you know how to code in Python? And that sort of kills their dreams in some ways, that they may be sort of these cool astronomers at telescopes. But luckily, as it was mentioned, I'm an instrument person, so I do still use telescopes quite a bit, and we'll talk a little bit about those in a couple minutes. But it's important, specifically this idea of how stellar variability and exoplanets relate to one another, because we have this saying where you want to know your star, and then you know something in astronomy. So if you wanted to know how galaxies form, you need to know how stars form, how they evolve, how they die. You want to figure out how, like, the Milky Way got to as big as it is, or as Andromeda looks the way it does. If you were just trying to figure out specifically like how our galaxy has evolved with time, you really need to understand the kinematics of stars. How are they moving through the Milky Way? What interactions are they having? How is dark matter and dark energy sort of affecting those types of objects and the merger history of the galaxy itself? That all goes down to understanding stars. And then finally, if we want to try to find physical properties of planets come from the physical properties of stars. And so if we don't know how stars are formed, what their physical properties are to very high precision, then all of that uncertainty in stellar models propagates to everything we know about the rest of stellar astrophysics. So understanding stars is super important. So a lot of the data that I want to talk about actually comes from this satellite called TESS, the Transiting Exoplanet Survey Satellite. So I did a lot of work on this satellite back about a decade ago, trying to target, so figure out which stars could be the next stars that would be good to find, like the next Earth or the next Neptune. The telescope launched in 2018. It's already, this slide says 100 planets. I think it's over like 500 now. with many, many thousands of candidates. So it's done a really good job finding planets. But again, this is a small telescope. It's about the size of a car, and the diameter of each one of the cameras is only 10 centimeters in diameter. And we have 4 of those. So it's a pretty small object. And to give you kind of an idea of just how good it does sort of looking at large swaths of sky, this is sort of a model of some data. So this is 1 degree on the side. You know, you see a couple thousand stars, sort of what you would expect in sort of wide field data. Each one of the pixels for TESS is 21 arc seconds on a side. So I like to joke that, you know, a lot of extragalactic astronomers, that's actually wide fields imaging is 21 arc seconds. But, you know, a typical wide field image is about a degree on a side. That's what you would expect. For TESS, their 1 CCD is actually 12 degrees on a side. So you move from thousands or so stars to hundreds of thousands of stars just in 1 CCD, but there are 4 CCDs on 1 camera. And so you quickly go from 12 degrees on the side to 24 degrees on the side. So it's big enough that if you were lucky and you were pointing in the right way, you'd actually be able to fit the constellation Orion just in 1 camera. And there's actually 4 of these TESS cameras sort of built in a longitudinal strip. So we can get 96 degrees whenever we're observing in the sky. Normally, I like in this slide, if I'm giving a talk somewhere, to also flip Orion to be upside down if like I'm in the southern hemisphere, and that usually gets a couple of laughs. But we're all in Texas, so I guess it won't work quite as well. Those were all kind of fake data, though. This is real data. So on the right here, this is a real image from TESS pointed, I believe, towards the galactic center. And so you see that there's like hundreds of millions of stars there just in a single image. And the way that TESS works there is on the bottom, it kind of scans in these longitudinal strips for about a month at a time, and then it moves around the sky. So it covers the whole celestial sphere in about 2 years or so. The whole idea of TESS was to try to find Earth-like planets around cool stars. And so typically the question comes, why were we looking for Earth-like planets, and why do we want to look for cool stars? So in order to understand why we wanted to look for Earth-like planets, we wanted to try to understand where the next Earth could be. So the question arises, where does life exist? And so where do we know that life actually exists in the universe? Well, we know for sure it's on Earth. Maybe there's other places in the solar system even, but we know for sure that life exists on Earth. We're all here. We're all having a good time. So that's good. We can check that off. And so what necessary compound is it for all life on Earth? Well, that's liquid water. We know that basically everything on Earth requires some form of liquid water. And we think some of the amoebas that were floating around, which sort of evolved into the current life as it is, probably started in the water and moved outwards. And so the question then says, well, where can we actually find an abundance of liquid water in the solar system? And we go back to the answer to the first question, Earth, right? We think probably Earth. We know for sure liquid water is here, but are there really any other areas in the solar system that we could be interested in? Well, we want to try to find out if there's sort of this region in each solar system where liquid water could exist, and maybe there's like a habitable zone. And so we think, based on how the solar system formed, that there's probably 3 regions in the solar system. First, there's a cooler region where most water is in the form of ice. So anything that landed on the surface of a planetesimal while it was forming became frozen and actually started to build up the larger planets. That's why we think Jupiter is as large as it is, because the sort of the solid rock that started off as Jupiter's core was covered in ice and allowed it to sort of maintain its primary atmospheres. We also think that there's a warmer region where if there was any kind of puddle on the surface of that planet, basically it would be immediately evaporated. And so we don't really see much of an atmosphere. If at all on Mercury, we don't see any sort of liquid water. But there's this sort of middle region where we would say liquid water water can stay liquid because we see it all over the Earth. And the big guy that's in the middle there is Earth. Now, usually, depending on how you define the solar system and the habitable zone, there's actually 2 other planets within it. I'm sorry? Okay. And so we can talk about those 2 to see if they also have liquid water on them. So the first one is Venus. Nice sort of picture of Venus here. So the question is, well, is Venus sort of a suitable candidate for life? It's roughly the same size as Earth. So if we went there, you know, we'd feel pretty good. We wouldn't have any weight changes. It rotates in the opposite direction of all other planets, kind of a little weird for other planets in the solar system, but it's still kind of a neat fact. It has 100% cloud cover, which would be good for me. You know, I live in Texas, but I sunburn through, car windows and sort of closed doors and stuff. So it would be good for me to be living kind of on a Venus type atmosphere. The problem is the surface is hidden from us by clouds of sulfuric acid. So it's not really habitable in our sense of something that would be useful for life like us. And of course, the surface temperature is near 900 degrees Fahrenheit. So, it's roughly about what Houston experiences in the summer. So we probably, as Texans, we'd be okay with that temperature. But the question is, it's suitable for life? The answer is really no. So you could define a habitable zone with an object in it that does not suitable for life. Second guy that's not Earth is going to be Mars. So Mars is roughly half the size of the Earth. So you would feel a lot lighter if you went there. It's a good way to lose some weight, I guess. If you can build a rocket, get all the way there, then you can lose that extra 20 pounds you've been trying to get rid of since Christmas. The polar ice caps are actually frozen water and carbon dioxide. So if we could figure out a way to melt those polar ice caps, we may actually be able to generate some global warming on the planet, which could make it more hospitable for us. Surface temperature actually feels pretty good. It's about 71 degrees in the summer and minus 81 in the winter. So the winter months would be pretty rough, but it would still be pretty cool during summertime. But it's certainly a livable sort of temperature range. And we're not sure, but there could be some seasonal water flows. So as we've looked at images of mountain ranges and things like here on the right, you'll notice that there are these kind of like fingers coming down the mountain. And it is possible that that is water that is freezing on the top of the mountain, and then it's rolling down. And then sort of as the seasonal cycles go, sort of ice freezes and melts. And if that's the case, then there could be liquid water that's existing on the planet. And if that's true, then it could be possibly a suitable candidate for life. So we've looked at these three different planets, all within the habitable zone. And so it really tells us that there's sort of a unique diversity within planets for what life could exist. But there's some nuance that's going to be involved that's going to be coming from the star that I want to talk about now. So that habitable zone for a sun-like star, we would say, well, that distance is probably about the Earth's orbit. So if we were looking for Earth-like planets around sun-like stars, if we wanted to find them with the method that we're going to talk about, it would take about a year because it takes 1 year for the Earth to go around the sun. If we were to look for a planet around a hot star, that planet's habitable zone would be super far out. And so if you were looking for planets around that star that were Earth-like, their orbital periods are going to be much longer than a year. So it's going to be a lot more difficult if you're crunched for time trying to find these types of stars and planets around them. But if you looked at a much cooler star, so these sort of red dwarfs, then their orbital periods of the habitable zone planets are going to be a lot lower, a lot smaller, because they'll be a lot closer into their star. So they'll orbit in periods much less than a year, sometimes just a couple days. And that's super useful, especially if you're trying to do a large-scale search looking for exoplanets. And so what's sort of the method that we're using? It's called the transit method. And so this is the way that I like to say that astronomy kind of moved into like a production line science, because we built a lot of these really small 10 centimeter, 5 centimeter telescopes, sort of put them all over the world and just stared at as many stars as possible. And so even before TESS, we were doing a lot of this work, and a lot of the work from the ground with these types of instruments really helped us to try to understand how the space-based telescopes would work, which was good because we were working on government funds. We needed to be efficient. And so how does the transit method work? Well, the planet slowly moves in front of the star, and if you're tracking its brightness with time, you'll notice a noticeable drop in brightness coming from the star if you're tracking it over time. And it would actually sort of look like this sort of box shape, because for these initial measurements, we can kind of just assume that the planet is just a rock in front of the star, and so it's just blocking a specific portion of light. This method, though, we see all the time from Earth, and it's basically an eclipse, right? We have when the moon moves in front of the sun, or the Earth moves in front of the sun, we can have either solar or lunar eclipses, particularly when the moon is between the Earth and the sun, and we get these beautiful sort of solar eclipses. It's really striking. So we were lucky enough to have 2 solar eclipses that occurred in 2023 and 2024 that went through Texas. So hopefully a couple of you guys got out to see them. I was lucky enough to see the annular solar eclipse just outside of Port Mansfield, Texas. It was super cloudy. It seems like whenever I go see eclipses that clouds just follow me around. But you can see there's a nice picture of my daughter, and my wife got to see it as well. There's this neat little sort of story that my wife talked about a dog sort of eating the sun has related to eclipses, and so that's what she said it looked like. Someone had taken a big bite out of the sun, which was pretty fun. But if you were to track the light from the sun in the same methodology with the same type of cameras, that signal, that box-like signal, is exactly what you would see. And so why are we looking at cool stars? Well, one is we want to be able to find periods of star or planets that are moving quickly, so we can find a lot of. The other is that this transit method, it's not difficult to do, but depending on which star and what planet you're trying to find, the signal for that transit can be small. And so the top here, this sort of shows how we're going to say, if we want to try to increase that transit signal, there's two things we could do. On the left, we could change the planet's radius. So if we kept the star the same size, but we wanted to look at for like Jupiter-sized planets or even larger, then that transit signal would be larger. The second thing you could do is you could try to keep the planet size small or the same and just decreases the star's radius. Now, it's a lot easier to ahead of time know what the star's radius is going to be than the planet's radius that you're looking for. We knew we wanted to try to find exoplanets that were like Earth-like, so the size of those Earth planets had to be a specific size. And so if we looked for smaller stars, then that transit signal would be much larger for the Earth-like planets. And so that was sort of some of the reasoning as well as to why we wanted to kind of target those cool stars. And so how did this test mission do? How good are we doing at sort of capturing planets? Well, these were all of the planets that were known before tests launched in the purple here. You can see there's a good distribution of them. And there's an interesting feature about this as well. You'll notice sort of the green line is about the size of the Earth or Venus. That blue line is about the size of Uranus and Neptune. As we started looking for exoplanets, most of the planets we found were actually in this weird super Earth mini Neptune size. And if you look at the total diversity of planets in our own solar system, so all 8 of them, we have a lot of really interesting, totally different planets, but we don't have any planet that matches this most common planet found in the Milky Way. So it's kind of an interesting feature of the solar system that we have so many planets and none of them are the most common. We've done a lot of work to try to understand whether or not this is like a bias that has been found or something we don't really know about our observations. And we're pretty sure that even if we account for those things, the most common planet in the Milky Way is sort of a very, very large Earth-like, Earth-sized mini Neptune planet. But these are the planets before tests. These yellow planets are the ones that were found after tests. So you can see we found a good number of objects that are sort of Earth and Venus size. That's good. That's what the mission was looking for. You'll also notice that the yellow dots have shifted to the left on this plot. And so the bottom axis, that's just trying to say how far away the star is. And so if the stars are closer to the left, that means they're closer to the sun. That means they're brighter. And it allows us to make a lot of measurements that are going to be useful later when we're trying to fully understand, is this a planet that could be habitable? Is this a planet that is just a rock floating around a star? And so it's useful in that way that all of these new planets that are found are very, very close to the sun. And so the other thing we like to look at is sort of this idea that planets are super abundant. We think something on the order of like 1.5 planets exist around any given star. I feel pretty bad for the people who are living on the half planet in a solar system, but that's the way statistics work sometimes. But if you look kind of through the sort of a distribution of stars, so this is just basically the entire celestial sphere. I've flattened it out. So on the bottom, we have right ascension in degrees, and on the left, we have declination. We can see that they're pretty well distributed. Now, there are a bunch of these little overdensities or clumps in the sky where we find planets. You'll notice that the one on the top right there is almost shaped like a plus sign. That has to do with a space mission that went before TESS called Kepler, and its CCD was in a shape of pluses, so it made this array. It turns out planets don't form in plus-size shapes in the galaxy. That would be really cool if they did, but that's just kind of an observational feature of how this was done. So what you're seeing is sort of all the areas that Kepler pointed in the sky, and that's why there's these weird areas with overdense regions. But going back to sort of the original idea of this talk, we want to talk about stellar variability, and we want to try to understand how do the observations of these Earth-like planets, has that informed anything about where life could be in the galaxy? So one thing about the easiest way to try to find whether or not an Earth-like planet is real as Earth-like, similar shape, size, atmosphere, so on and so forth, is we can do this method where we try to measure the atmosphere. And so what you're seeing here is a plot. Basically, it just shows a bunch of lines. The two on the top mean the planets have no atmosphere. The two on the bottom mean there is an atmosphere. So it's sort of a basic way. The problem with a lot of the initial measurements we made of sort of these small Earth-like planets that are orbiting around these cool stars is that it looks like a lot of them, if not all of them, have no atmosphere. And that's because a lot of these very cool stars are super active. So when the sun sets off a flare and we lose internet or a satellite for a couple hours or something, it's not a big deal. But these cool stars flare, tens, hundreds, thousands of times more intense than the sun. And they do it quite often, sometimes multiple times a week, sometimes multiple times a day. And so planets that are Earth-like, that are constantly subjected to this type of level of intensity coming from the sun, can actually strip a lot of the molecules from their atmospheres. And so it's possible, even though we found a lot of Earth-sized planets, they're not actually Earth-like because they don't have an atmosphere. They don't have liquid water on the planet. And so now we have to kind of reverse engineer a lot of understanding about what's going on with these cool stars and their variability to understand if we can really know if they're Earth-like or not. And so how are we doing this? Well, there's a couple ways. So all those small telescopes we talked about before, we've done a lot of surveys looking for variable objects. And so this was a survey I was involved in called KELT, the Kilodegree Extremely Little Telescope. And these are basically all the variable objects that we found. So we were just looking at the brightest 4 million or so objects, and we found about 50,000 classically variable objects. And so when I say classically variable, I mean things that we probably knew were variable stars earlier. So these are some light curves of them. So this on the bottom, the amount of time that telescope has been observing was upwards of almost 20 years in some cases. So we had observations of stars that lasted a really long time. And sort of the one that I want to draw your attention to that is really cool is the one in the bottom middle. And so this is some star that was just kind of chugging along, really not showing brightness changes. And then some sort of large disk or something moved in front of it and actually dropped its brightness. So we think it was some type of debris disk or cloud in the system. We also show a bunch of stars that are sort of going in variability with time, like these classical Miras and things. And then, of course, we find a lot of objects that are known quite well by amateur and professional astronomers, eclipsing binaries, RLIREs, contact binaries, Cepheids, all of these fun objects. So there's a lot of stuff in the sky, even if you just look at the brightest stars in terms of variability. And so we really need to try to understand what's going on in a lot of these solar systems. Because as something like this can show, you can actually have stars that are variable, not just in timeframes of like 100 days, but in timeframes of like thousands of days. So if you just look at a star once, say the object in the middle, and you just look at sort of one little peak area for even, I don't know, 100 days, where it's not having this eclipsing debris disk in front of it, you may say, okay, well, nothing is really going on there. And then you may look at it 2 years later, and totally the magnitude is different. It's fainter by 3 or 4 magnitudes. It's really something is going on. And if you haven't really been observing it constantly, you won't know that there's changing. You may think that there's something wrong with your initial measurement. So it's important to study that. So really the problem we're trying to solve was how can we ensure that we're properly accounting for how stellar variability is affecting all of the exoplanets that we're looking at. And so there's sort of 2 ways to do this. One is to study the variability of multiple stellar populations, and the other one is to try to study the atmospheres of many exoplanets as possible. So why would we want to look at sort of the variability of stars? Well, on the left here, this is called an HR diagram, and it's just a way that you can try to determine whether a star is young or old in some ways. And so if it was in the top right there, where they have that big circle, that's sort of where you expect like RLIREs and eclipsing or Cepheids, sort of anything that's pulsating. Then anything on this main sequence here, those are stars like the sun. You don't really expect them to be variable. They should just be hanging out, not really doing much. And so if you're trying to look for planets like Earth, you'd want to target the stars that are like the sun. The problem is if you target stars like the sun, they actually have variability cycles that are different as well. If you look at our own sun, we know that its variability cycle is, we study it pretty well, but we don't have a great understanding exactly of some of the dynamics that are involved. And so we have to really study these types of stars, understand how their variability is changing, which is how you see sort of the plots on the left, because it looks like, depending on its rotational period, there may be some sort of change in variability that's affecting that star. And that also may then change its ability to have an Earth-like planet around it. And we're only able to make these really, really precise measurements in really the past 2 years, 3 years or so, with telescopes like TESS and things like the James Webb Space Telescope that was just sort of launched. So we're really kind of on this cutting edge now of understanding, okay, the star flickers in this way or it flares in this way. How does that represent how life could exist around the planets that we're looking at? And so really by looking at as many planets or stars as possible, looking for planets, that's told us something about sort of the inherent variability of those solar systems. We don't really fully understand it yet, but we're trying to sort of track it down, which is sort of fun. One way that we're doing it is actually trying to make sort of a very large catalog of all of the known classical variable stars in the sky, understanding what their pulsation cycles are like, trying to understand, their time of maximum brightness, what their periods are. So we can then later go through and say, oh yeah, these stars are being affected in this way, or they're nearby objects, or these biases are affecting our sample. So it's pretty neat, kind of taking older methods in astronomy and then applying them to the new data. The second way that we can try to understand sort of how exoplanets are being affected by their star is by studying a lot of atmospheres. And so now I'll talk a little bit about, in the last 10 minutes or so of the talk, sort of about how we're doing that from Texas and some of the instruments that we have. So the way that we liked, or the group that I work with likes to think about this, you have to take a little bit of a step back. And so the first discovered exoplanet, which I think now, the first discovered exoplanet around a sun-like star, I should say, which I think now is almost 30 years old, was this Jupiter-sized planet that was super close to its star. So in this sort of cartoon representation here, which, as you can tell, I've made all of this artwork in PowerPoint. So if you like my work, I'm happy to do a painting or something for you. But this Jupiter here, it's on an orbit that's only 4.5 days. Mercury has an 88-day orbit. So this is way, way closer than the orbit of Mercury. But it totally broke the mold and destroyed what our concept of planet formation had to be, because we originally thought it was very similar to our own solar system. All the gas giant planets are in the back. All the rocky planets are close to the sun. But the fact that one of the first objects that was found was this sort of Jupiter-sized planet immediately meant we had to totally rewrite what we understood about planets. To kind of hammer this point home, one of these sort of really hot planets is called Kelt 9b. So this is one of those hot Jupiters. It's orbiting around an A or a B star, which is super hot, much, much hotter than stars like our sun. And it's on a polar orbit. So instead of orbiting west to east, like the objects in the solar system do, this thing is going, north to south. And so clearly there's some weird dynamics of the solar system that started and formed this sort of weird dynamic between the star and its planet. But the interesting thing about this system is 10, 15 years before the planet was found, if you would have tried to convince professional astronomers, I want to go looking for hot Jupiters around these really hot stars, you would have gotten feedback that said, you shouldn't do that because A, B star, they're so big, they take up all the mass of their solar system. Any material that would have made planets would be pushed out by their stellar winds, and you're just never going to find a planet around them. But of course, the easiest thing to do if you want to find something in astronomy is say it doesn't exist in the universe, and then within a couple of years, someone will find it for you. So it's always important to not give up on the type of stars that you're looking at, because you could really pigeonhole yourself into understanding how, some interesting thing about astrophysics. And of course, the most important thing about the discovery of this object, Kelt 9, was that Captain America, back when he was on Twitter, actually tweeted about it when it came out. And so we always like to say that's sort of or at least Scott, the author of the paper, says that that's the more important thing. Not that it was written in Nature, but that Captain America got to read it, which is pretty fun. Okay, so how do we then try to target these weird hot Jupiter objects to understand formation? And that's to look at their atmospheres. And so we use basically the same method we did to find them, but we change it slightly. So instead of just looking using like white light, we decide we're going to look at the star in two filters or multiple filters as the planet is moving in front of the star. And so depending on the molecular makeup of the planet's atmosphere, the light in the blue during the transit will look different than the light in the red. So you may see a deeper transit in the blue than you see in the red. And that actually tells you something about the molecular makeup of the atmosphere. The difficult thing about this is that the equipment you need to make these measurements is super costly, and it usually needs to be in space or on a really large telescope. And so on average, that's about $50,000 an hour you need to spend in order to make these measurements. So you can't really do this on a large scale like we were doing with tests. You have to be very specific on how that's done. What's worse is if you look at a bunch of the atmospheres of planets, basically there's no correlation to them. So on the left here, we're just looking at the way that the atmosphere of a planet looks at different wavelengths. All that's important about this figure is just the fact that a lot of those squiggly lines don't look like one another or they're flat. And that means that we don't really know what's going on in those atmospheres. It could be that they're getting too much irradiation from their star. It could mean that the equipment isn't working. It could mean that we don't fully understand planet formation. It's likely all of those things combined. But it means that we have to get creative in how we're going to be studying these types of objects. And so how can we obtain transmission spectroscopy of all these exoplanets? Well, we actually developed this new imaging technique called common band multipath imaging. So the way that this works is if you were to, if you've ever done sort of like old school prism spectroscopy where you literally just use a prism and then you try to, you shine the light from the prism onto a CCD or a plate, and you look at the different wavelengths and then you can understand what the spectra looks like. That's basically what we've done, except we have a filter now just after the prism that breaks up the light. So we know specifically where every wavelength is. The other interesting thing about this method is that all of the light you're seeing in each one of these little dots here has the exact same systematics or all of the issues with it that come from ground-based observing. So that light traveled all the way from its star. It went through the Earth's the planet's atmosphere, came into our solar system, went through our atmosphere, hit the mirror on our telescope, went through the instrument, and then it gets split by the prism and the filter. And up until that point, the light traveled through the same path. But then once it hits the filter, it gets separated into its wavelengths. And so the fact that we know that the light went through the same path every single time, it means that anything that is common between all of the wavelengths, we can just remove it because it's not what we're looking for. We want to understand how things change. Remember, we want to know like that red transit. How does the red transit look different from the blue transit? So if one of the filters like 937 looks different from 533, we immediately know, oh, that difference has to come from the planet itself, which is pretty cool. And so this is what the instrument actually looks like. So it's not super complicated. We have a computer there on the right, or sorry, on the left. The prism and this sort of weird filter that we have is in the center capsule there. And then we actually use two CMOS detectors, which is pretty new for astronomy. A lot of folks have been using them for astrophotography as well as like meteor observations. But we're using them sort of in a scientific instrument for the first time in our own lab, and we're trying to convince more people to use them because they're really great. They let you do sort of very, very high cadence observations, and they really come out pretty clean, which is pretty cool. So this is sort of what an on-sky image would look like. So on the left, this is what the normal night sky looks like. On the right, this is what our instrument looks like. So again, if you know what sort of the old school prism spectroscopy looks like, it looks very similar to that, where you have red on one side and the blue on the other. This this instrument's out at McDonald Observatory. So we use the smaller guy on the left there, the 2.1 Otto Struve telescope. About 60% of the nights are clear. If ever get a chance to go at McDonald, I highly suggest it. It's a beautiful place. This is what it looks like when you get good weather and you can really see all the stars. They're amazing to see. Unfortunately, as I mentioned earlier with the transit stuff, clouds like to follow me around. So normally when I go out there, it looks like this. That's okay though. You know, I work through it and we still get some good observations. But the Otto Struve telescope is pretty cool because we're doing these planetary atmospheric measurements, but it was used by Kuiper in the 40s actually to take observations of methane in Titan's atmosphere. So it did a lot of the same stuff 80, 85 years ago. The cool thing about this telescope as well is that it's so old. And so it's really like a lot of history when you're using it. We were able to get over 100 nights on the telescope over the past couple of years, so we were super lucky about that. And the project that we worked on had more than 24 students. So I always enjoy including students on projects. It's really nice to teach them something about astronomy and to be able to get use such a big telescope. So what does the light curves look like? So this is real data now of a transit. On the top is the method that we use. On the bottom is sort of the conventional method. And you can see that sort of transit shape looks very similar to a lot of the toy models I drew in PowerPoint art compared to the one on the bottom. So we do a much better job. And that's really allowed us to understand how the atmospheres are for a bunch of different planets. So this is sort of the nice example I like to show. So in the red are observations from the Hubble Space Telescope. In the black are observations we made with a 90-year-old telescope from the ground using our instrument. And you can see that, there's some difference between the two lines, and, one is a little bit higher than the other in some spots, but the general shape is there. So we recover basically the same features in the atmosphere, which is really nice. The biggest difference between these two lines, though, is the cost. So the red line took about $800,000 to make, and the black line took about $160 to make. So clearly we're doing something better, at least trying to save money. And we're able to use this instrument now to take a lot of observations of planets very quickly for very cheap. And this can be something that's done sort of just on a sort of a normal grant cycle, which is really nice. I did want to mention that we use this instrument for a lot of other objects as well. So we look at just kind of like standard stars, and we get very, very flat photometry, which is really cool. I think the standard error of some of these light curves is like 0.006%. So it's super, super small. It's really nice color photometry. We've taken a bunch of different observations. So there was an occultation of Titan back in 2022, which we observed. So you can see Saturn there is on the bottom right with a couple of moons, and then Titan and the star that it went in front of. This is what that data looks like. So on the top here, you have Titan and then occultation on number 2, and then as it moves back out from the star on number 3. And that's the time series there on the left. So where you see that transit occurring is actually where Titan moved in front of that star and the occultation occurred. And so we think we've detected methane with this method, which would be pretty cool to, again, sort of redo the measurements that Kuiper was doing as well, which is pretty nice. We also have a lot of observations of variable stars, including observations of stars that really haven't had color measurements before. So again, that's observations at one filter and another filter. So like these crazy rotating white dwarfs that have these periods on the order of like a couple of minutes or something, and they have sort of changes in their brightness with time because there's a lot of stuff going on. No one's really made these types of measurements before. We actually don't really know how to interpret them yet, which is pretty cool. We also have observations of just kind of like general binaries, variable stars. So eclipsing binary on the left. We have an RL Lyrae on the right, which is pretty cool as well. Sort of shows what we would expect in terms of the change in the amplitude in the blue compared to the red. But again, these are such precise measurements that the little wiggles that you see in a lot of light curves, we think are genuine. And so trying to understand what's going on from, on a 5-minute time scale on an RL Lyrae surface is really interesting, but it can help us to understand things about solar systems in the future. And then, of course, as I mentioned, we get a lot of students involved in this work. And so we've also started looking at things like planetary nebulas, so these clouds in the sky of former stars as they sort of push their atmosphere away. And 2 students that I worked with at Texas A&M were trying to do some machine learning to see if they could immediately categorize what elements were in the planetary nebulas. Because again, ETSI just basically needs to take one image immediately, and you get a lot of information about the object. So it's pretty cool. We also have a student who's looking at these weird brown dwarfs as well, trying to understand variability. So brown dwarfs are these objects that are not quite stars, they're not quite planets. They fit in that nice realm of what happens when a star isn't big enough to burn hydrogen and helium. And she also is trying to understand, is there some effect from the star itself that helps to understand why these objects look the way they do? Because they're between like stars and planets, they have weather like Jupiter does, but they also have star spots like the sun does. So it's just weird. We don't really know what's going on. And so we're trying to understand sort of how things are changing on very, very small timescales. With these methods, though, we were actually able to do some initial estimates of how the stars could be affecting their planets. And it looks like things like the types of elements in the star actually force the way that the planet looks. So the star that has more elements, more what we call metals in it, heavy elements, not hydrogen and helium, could mean that you would likely see planets with things like titanium oxide or sodium or potassium in their atmosphere. And so again, this is very tentative things, but we were able to get so much time on a small telescope. We were able to make measurements like the Hubble Space Telescope, and then we were able to try to understand what's going on in those planets in a much more conventional way, much cheaper way, and hopefully we'll sort of crack this thing, and then be able to use instruments like the James Webb Space Telescope to really fully understand what's going on with their sort of high precision. So I'll just end sort of saying, where are we going in astronomy with these kinds of things? So that mission I talked about, TESS, that is basically going to continue, we think, for the next 10 years or so, assuming that it continues to get funded. The James Webb Space Telescope, this is doing a lot of like dedicated follow-up. It makes those really nice pictures of things because really high precision. We can really target planets and understand what's going on in their makeup. Then there's a big survey called Rubin LSST, which is going to start at the end of this year. It's going to understand how like stars explode and how the sky is dynamic with time. So that'll tell us just how stars can change with time, which is a lot of fun. And then as we look towards the future, there's things like Nancy Grace Roman, which will look at a lot of the stars in the galactic plane we haven't seen before. And then if we're lucky enough, in 30, 40 years, the 30-meter telescope and the Giant Magellan Telescope, GMT, TMT, may come online, and then we may be able to actually look at specific star systems instead of doing a lot of the work I talked about in the beginning, where you infer something from a star. You can actually target a planet itself and actually study the planet. So it could be a lot of fun. Hopefully we'll get there. I think that I'll probably end there though, and see if there's any questions. But thank you guys for giving me the opportunity to talk.
Dr. Oelkers, I've got a question. Do you use any of the data from amateurs from the AAVSO side?
I have the use of the AAVSO site, right?
Yes.
Yes, I have used them before. That mission we talked about, KELT, we've used that to help understand some of the planet candidates we had. But I also, when we were originally looking through and finding all those variable stars, we initially went back to the AAVSO databases to see what had been discovered. It helped us to identify, when we were trying to understand, like, is this an R. Lyrae or is this a Cepheid or something? We could use data from, the past 10 years, 20 years to say, oh, okay, yeah, they get it as an R. Lyrae too, and then we should use that. It's also useful. A lot of those weird objects that I showed that like are kind of flat for a decade and then they drop for 5 years and they're flat. A colleague of mine, Joey Rodriguez, has used a lot of that data to try to fill in the gaps to say like, oh, it's also dropped 15 years ago or 5 years before KELT started. So, but yeah, we use that all the time. It's super useful.
Nice question. Can you hear me if I just Okay, you made several points about the cost of various platforms. I see the Rubin LSST, I think it's supposed to come online in July. When it comes to using that, you have to be worried about what the cost is of a telescope like that?
Yeah, I mean, I guess we did a couple of years ago. I think, and I could be wrong, I think a lot of the funding that's used for Rubin LSST has been allocated already. So once they get sort of past their initial couple of years of their prime mission, then whether or not they're going to continue to fund it over time may be a question. But usually once we get to a certain point where like a telescope's built and it completes its survey, then it kind of does open calls for funding or changes its mission in a sense for how we can observe what we're going to observe. It was certainly an expensive project, and I think it's going to do great things. And I think its funding should be secure for a while. I don't know the ins and outs of it, but I think it should be safe for a good amount of time.
Okay, thank you.
Any other questions?
Chris Morrison has some, he wants to
come off mute? So
Yes.
please come off mute.
I'm here. Do I have the floor?
Yes. Yes, sir.
Okay. Hey, great presentation. Two questions. The hot Jupiters, why isn't the atmosphere of those just burned off or evaporated very quickly? What keeps the atmosphere intact? That's question one. And then question two, the Hobby Eberly telescope has spectrometers that actually look for habitable zone atmospheres. Do you utilize that equipment at all or anything of that nature? I was curious about that. Thank you.
Sure. Yeah. So the first question. So I hopefully you guys can see the sort of the planet spinning around a star again. You'll notice that there's a cloud trail behind it. So these objects do, in a lot of cases, depending how close they are to their star, it will actually start pulling the atmosphere off. And so as time goes by, eventually that object will just totally lose its atmosphere. It just takes time for these things, and something that may even be quick on astronomical timescales, like 1,000,000 years. It just, for us, it takes, it seems like it's taking a long time. And so we're able to still observe these objects with their atmospheres intact. Now, that doesn't mean that every hot Jupiter is going to lose its atmosphere. It really depends on how close it is to its star. It depends on how hot that star is. Depends on if the planet is tidally locked and all of these other fun things that go into it. But we do see evidence that planets their atmospheres are being ripped away if they're too close to their sun. But in a lot of cases, they're just so big that they're able to maintain a lot of that atmosphere better than something like Mercury did. Your second question about HET, I have used some of the high resolution spectrographs on there before. Right now, the way that HET is set up, it requires a certain level of participation from an institution, I believe, to be able to use the instruments. And so that's why I don't use it very commonly. But again, it's also an instrument that has a lot of competition for the time that it's allowed to observe. And so because of that, it's a lot easier for us to, it doesn't seem like it, but in a lot of times it's a lot easier for us to build a new instrument, put it on a telescope, and then use that telescope if it's smaller. Because like I said, we got 100 nights, and if we wanted more, we probably could have gotten more because we were lucky enough that that telescope wasn't used as much sort of in the past couple of years. And so that's why we don't necessarily use it. But if we wanted to, we would, but right now I just don't use HET. But it's a very good telescope, I have to say.
Okay, sorry, you muted. Yeah, we thank you, Dr. Oelkers, for opening our eyes up to the complexity of the variable stars, and they're not just as simple as just stars dimming and brightening. There's a lot more involved to it than we think. So very, very fascinating presentation. Thank you very much.
Thank you, guys.